Hey, Marcus House with you here. Today I thought that I would compare the Falcon Heavy to something much larger, the Saturn V. Here it is in all its glory. Now, it's easy to actually see here just how massive the Saturn V was in comparison to what we've all seen as the largest currently operational rocket, the Falcon Heavy. So when we actually zoom out, you can see there the Falcon Heavy really only comes up to the top of the second stage of the Saturn V. They're quite monstrous. The Falcon Heavy there coming in at around 1,470 tonne, whereas the Saturn V coming in at 2,980 tons, so basically double the mass there. What we're going to do is launch both of these together at the same time. Both engines are fired up, and you can see there that the SpaceX Falcon Heavy is already past the height of the Saturn V, leaving it in the dust. The thruster weight for the Falcon Heavy there is just so much higher. And if you recall watching the old footage from the Saturn V's taking off, the Saturn V really did launch very slowly. The thruster weight at takeoff was around 1.15, I believe, from memory. After a very short period of time, we are already around 10 kilometers above the Saturn V. Pretty amazing actually to see just how much thrust to weight the Falcon Heavy has there in comparison. But what we're actually going to do today is do the historic flight here with the Saturn V. We are doing an Apollo mission, and we just need to make sure that our launch window is correct. So what we want to do is launch just as Cape Canaveral passes under the orbit line of the vessel we have in orbit, which is exactly matching the inclination of the moon. So we just need to time warp until Cape Canaveral here passes underneath that yellow line. So about here, and you'll see we have our 3 Kerbonauts. This is Kerbal Space Program that we are simulating this mission in, so they are tucked away in the command module, and we just need to wait now, just very slowly time warping until that relative inclination here gets to as low as possible. We only really get to around 0.26 before we should launch, and that's going to give us a very close inclination with the moon when we get into orbit. So the launch window here has finally arrived. It is time to ignite those 5 F1 engines. So our first stage has fired up. It is on its way. We've obviously got this footage sped up quite a great deal, otherwise this would be a very long video. So we are just launching through the typical launch profile that we would generally see in a mission like this. This simulation is done using the RealSolarSystem and the RealismOverhaul mods for Kerbal Space Program, so it's actually quite close to what we would see in real life. It's using a very close model to the real Saturn V, so all the thruster weights, all the stages are very accurate compared to what we would actually see had we have been watching this in real life. We have main engine cutoff of the first stage. Firing up the second stage there, using those ullage thrusters to basically allow the vessel to separate cleanly while keeping the fuel pushed to the bottom of that second stage, and then we can just ditch that interstage there, just watching that fall away nicely just after the 5 J2 engines there on the second stage fire up. So our orbital velocity at this point is just around 2,500 meters per second. We have a long way to go to get to orbit. We don't need the launch escape system at this point in time, so we can ditch that off. That was essentially used just in case the first stage of the rocket failed. Now the stage 2 here had a dry weight of around 36 tons, so that's without any fuel in it, and then fully fueled is around 480 tons. So the second stage accelerated the Saturn V here through the upper atmosphere, and this essentially pushed the entire vessel to around 6,500 meters per second. So orbital velocity is just shy of 8,000 meters per second, so the vast majority of the way there. Now we are almost out of fuel with a second stage. There we go, second stage cut off there, and we'll just time warp up and do our separation quite close to our apoapsis here, just to make sure that we're not incurring too many gravity losses there. Again, using some ullage motors to cleanly separate the 2 stages and engage that single J2 engine on the third stage here. Now this J2 engine is exactly the same as the J2 engines that were on the second stage. Obviously there was 5 of them on that second stage, just the single one here, which is now going to push this third stage up to orbit. After that, the engine will of course shut down, and we need to wait until we are in the correct position to do our translunar injection burn, which is going to push this entire stage all the way up to intersect with the moon's orbit. Now we're going to be finalizing our burn here by circularizing at around 300 kilometers in altitude. You can see our apoapsis height here. We are currently at 300 kilometers, and as our orbital velocity gets up to around 7,700 meters per second, we should be around circularized, and there we go, 298 kilometers there for our periapsis height. Perfect. The next thing we need to do is set up our translunar injection burn. So we need to do it at the right time to make sure that our vessel is going to come in here just in front of the moon so that we get our free return trajectory. This means that if for some reason something goes wrong with our vessel, then we can get all the way back to Earth and re-enter the atmosphere with basically no more energy spent, with the exception of probably a few tiny corrections with our command module on top there. We shouldn't need to do that today though, because this is going to be the perfect mission. Nothing fails in Kerbal Space Program, so we are all good. Now the mass of this vessel remaining is around 130 to 140 tons. Now this is the maximum payload that was capable of the Saturn V, and if we compare this to the Falcon Heavy, that in a fully expendable configuration, that means we don't return any of the boosters, we use all the fuel, and this gives us a maximum payload of around 63 ton to orbit. Now that is more than double what the capability of the Falcon Heavy currently has there for us, so we cannot underestimate just how massive the Saturn V here was and just what it could do. Now, after the translunar injection burn and a little coasting, it was now time to extract the lunar lander and dock it with our command module. So we can see the petals here opening up, and we can then turn around and dock with the lander. Now, for those of you that aren't overly familiar with the Apollo spacecraft, it essentially had 3 components. It had a command module, which is the capsule there on top. That is where our 3 astronauts there are currently held up. The command module there is then docked onto the service module. That is the whole part we can see spinning around here. That had all sorts of little components to it, the RCS, the oxygen, the water, electrical power, all that sort of thing. And this whole part here now comes into dock with the lunar module, the LIM, and this has 2 stages of its own. It has the descent stage, which is the part there with the gold foil. It's got the landing legs and that sort of part that is currently attached to the top there of stage 3. We're going to extract that here shortly. And then the top component of it was the ascent stage, and that would get the astronauts all the way from the lunar surface all the way up back into orbit. So we've just decoupled that there, and we'll slowly use the RCS to extract out the lunar module in its entirety. At this point of time, we need to switch on all of the electrical gear, the air filters, the fuel cells. Everything needs to be turned on here to make sure that our astronauts are going to survive the journey. In the meantime, what we can do at this point is do a very small burn with the tiny amount of fuel that is left here with this third stage. And what we can do is ensure that that's going to impact on the moon's surface. Now, this wasn't done with all of the Apollo third stages. In the Apollo 8 mission, the very first mission to fly to the moon, essentially put this stage on a flyby trajectory that had it out in a solar orbit after it had left the sphere of influence of the Earth. Apollo 13 and 14 specifically, they were deliberately crashed into the moon, so that's what we're doing in this mission. But before we do that, we need to first do our very small correction burn, our mid-course correction. Only 29 meters per second burn needed to be done here, just to bring our main lunar lander vessel and command module down so that we're doing a very low altitude flyby. And this is where we're going to do our retrograde burn to bring our vessel into a low lunar orbit. You can see a glimpse there of the stage 3 coming in afterwards, about to impact on the surface of the moon. We'll watch that in a second, but first we're going to fire up our service module's engine, the AJ-10, and with the very low thruster weight, we need to reduce 830 meters per second of velocity to drop ourselves right into a low lunar orbit. In the meantime, of course, we can watch our third stage here impact very dramatically on the moon's surface. Impact speed here is around 2,500 meters per second, so quite an impact there. Meanwhile, our 3 astronauts are doing all the final checks they need to do before getting into that lunar lander and heading down to the surface of the moon. Only 2 of the astronauts, of course, are hopping over into that lander while 1 stays back in the command module. In this case, we are going to transfer Jebediah Kerman and Bill Kerman over into the LIM, and poor Bob is staying back. He's going to be very disappointed to not be one of the 2 that are going to be heading down to the surface of the moon here. Some beautiful shots as well from the hull cameras that I've placed on the vessels here, just so that we can watch the docking and undocking processes here as they occur. So Jebediah and Bill Kerman, they have opened the landing legs. We're going to engage this descent engine. The descent engine has just enough fuel to make it from a low lunar orbit to the surface of the moon. Starting off here, we need to wipe off over 1,600 meters per second and of course fight the gravity losses as we come down to the surface of the moon. We just did a preliminary burn there just to make sure our trajectory was going to bring us down to the surface, and as we get close to the surface we need to engage those engines and start reducing our velocity to come down to land. Now, although we've talked previously about the Falcon Heavy not having the capabilities of the Saturn V, there is certainly possibilities, future possibilities, that could get vessels to the surface of the moon. If you want to check out a previous video I did here, I basically did a double drone ship landing and also launched a very large payload to the moon, so check that out. And then we did another mission where we used a few Falcon Heavies and a Falcon 9 to construct a vessel that is capable of landing on the moon and do a full manned mission returned. So just coming down to the surface of the moon, just ready to touch down. And there we go there, touchdown on the surface. A little fuel remaining now. That fuel margin was needed because in the Apollo mission there was a little bit of coasting needed before they could find a suitable site to touch down. So Jebediah Kerman here taking one small step for all Kerbal kind on the surface of the moon there. And of course the next step in our process here, as always, is to plant the ceremonial flag. We have the NASA flag here today to celebrate the lunar landing. Our second man on the moon, of course, is Bill. Come down, Bill. We're going to waddle you over here. You can take a little photograph here with Jebediah and the flag. There we go. And given that this is our very first Apollo mission, we need to do all those wonderful science experiments that all of those in mission control are telling us to do. So up you go, Bill. You can pop back in, do those special experiments, and after all this is done, we're going to head back up and dock with our command module. Now, in order to do that, we need to make sure that our command module is orbiting over the top of us in the correct placement. So around here seems to be around the right launch time. So again, we have a very important launch window, otherwise it's going to take us way too long to intercept with our command module. So beautiful shot there of the ascent stage taking off, and we can see the descent stage there still on the moon's surface, slowly fading out in the distance. Now, the ascent stage of our vessel only had a mass of around 4.6 tons, so very, very tiny in comparison to everything we've been using so far. So although there's only a tiny amount of fuel in this ascent stage, it's got enough delta V, that's the change in velocity possible, to get us all the way back up into a moon orbit and intercept with our command and service modules. Surface speed currently here is just over 1,300 meters per second, not that far to go now to get up to our intercept, and you can see our apoapsis marker there just crossing the altitude of the command and service modules there. Now I can just do another quick correction here just to increase our velocity and pitch down just a little to make a much closer intercept much sooner. Now this probably wouldn't have been done in real life. I suspect the timing would have been just much better than what I did, but I had the delta V available to me to actually make this intercept, and then I needed to obviously wipe off all of the relative velocity as we were passing by the command and service module there. So there we go, we've reduced all of our velocity and we just need to do a very small correction burn just towards the target and just again turn retrograde, and we'll just wipe off that velocity as we get real close and then we can start performing that docking maneuver to actually attach the two vessels back together there again. Was just coming up a little close there. There is no way in real life that they were heading towards each other at 16 meters per second. That would have been crazy. But you know, this is Kerbal Space Program, so we can pretty much just quick save and quick load if we happen to smash into it. And as well, just to be lazy, I'm simply able to turn both vessels around using the RCS jets and basically both point them at each other, just so that I don't need to worry about which direction I'm approaching the vessel from. So there we go, we can see those docking cameras beautifully showing that scene of the service module and the limb connecting back together again, very close. And there we go. We can of course now transfer our two very brave astronauts, Jebediah and Bill, back over into the command module. We'll just detach that ascent stage, and essentially these ascent stages, or some of them at least, were used for seismology. Once the landing crew had transferred everything coming back to Earth from the landing module and closed it out, the now useless spacecraft was jettisoned and directed by mission control to impact the moon's surface at a specific point. The seismic readings of all this on the moon were very interesting at the time. Of course, the moon being so dry, any vibrations lasted for much longer than they do on the Earth. So there we go, we've smashed that ascent stage into the moon's surface. We can now prepare our command and service module to begin its burn to escape the moon's sphere of influence. We're just setting up a quick maneuver node here to simulate how we need to do this. We essentially want to escape and also drop our periapsis around the Earth right down so that we will be right near the atmosphere as we hit the periapsis point in our orbit around the Earth. So we've just started our burn there. Almost 800 meters per second is needed to get ourselves on the correct trajectory to return to Earth. The astronauts in real life, of course, had a time limit with everything they needed to do. They had food supplies, water supplies that could run out. They also had an electrical power system which could run out as well. And the 3 fuel cells that were on board the service module here would eventually run out of power. Time warping in now, we are very, very close to entering the atmosphere here. We can now detach our command module here in a moment. Before that though, we just need to do a few very small corrections just to drop our periapsis height to make sure that we're entering in here at the correct height to ensure that we're not going to skip back out of the atmosphere and head back off into space. If this happened, of course, our astronauts may not have enough fuel and energy to get back to do a second re-entry attempt. So just to be sure, I have set the periapsis here to be around 39 kilometers. This is more than enough to ensure that our command pod is not going to skip back out of the atmosphere. It's going to be hitting the atmosphere very, very hard actually. You can see the surface speed readout in the nav ball in the bottom left is climbing very rapidly. It's going to get right up over 10,000 meters per second. That is extremely fast. Of course, orbital velocity is almost 8,000 meters per second, but then add the extra velocity we needed to get to the moon, and we now have over 10,500 meters per second to wipe off relative to the surface of the Earth. So we're just re-entering the upper atmosphere here now, just passing 70 kilometers. You can see the heat shield on the command module there just glowing white hot as the plasma flows over the top of it. We are decelerating very, very rapidly, of course, and you can see the G-force meter there in the nav ball just climbing up to the maximum. Probably a little more aggressive than what the real re-entry profile would have been, but I wanted to make sure that we were going to get down to the surface in the one pass. So we've wiped off the vast majority of all that velocity. Our surface speed now just a few hundred meters per second. As we slowly fall down, we're going to deploy our chutes here, and then we get to finally see that iconic shot of the command module here slowly floating down with the 3 massive parachutes that are deployed here just above the surface. Of course, in real life, again, we splashed down in the ocean, but today we're just going to touch down very nice and gently right on the surface here on the ground. And there we go there, a very safe return and a very successful mission. Now, just so you know, guys, I've got a new Discord set up and have got a growing community allowing us to all chat more directly. So if you would like to be involved and you would like to chat, there is a link in the description below. I hope you enjoyed that video, everyone. Please do take a second and hit all the various buttons and things that you've got to press these days to get notified of my videos. All your support is just awesome. If you have any questions for me, please do whack them down in the comments below. If this video has earned your subscription, welcome to the channel. And for all the existing subscribers, thanks for being so awesome. In the title in the bottom left today, we have my previous mission where I show how I would re-enter the stage 2 of the Falcon 9 here with this heat shield. In the top right is my latest video, and in the bottom right, a video that YouTube has chosen just for you by some insane robot. Thank you for watching, and we'll see you all in the next video.